Hello and welcome. This is Lex Paulson of the UM6P School of Collective Intelligence and Sciences Po Paris. And in this series of videos, you're going to learn about some methods of using collective intelligence to solve the world's most complex problems. We begin with an old story told different cultures about six old men, or in this case, six rather healthy-looking scientists. And these are six very diligent, very intelligent, very motivated people. But as you can see, they all have blind spots, and they're encountering this big, novel, never before seen object, and they're gathering data on what it is. And one of them touches kind of a pointy thing and says, "Oh, I know, this is a spear." Another one touches a big floppy thing and says, "It's a fan." Another one touches a huge solid thing and says, "Oh, it's a wall." So you see, each of them is right, is correct. But unfortunately, all of them individually are wrong. So this is one way of thinking about collective problem solving. We all have information, but we all have a partial view of a problem, especially when the problem gets more complex. And so since we all have partial information and blind spots, we can help each other complete the picture. Groups have unique talents. This is what our science of collective intelligence is dedicated to studying. One is that one of the unique strengths of groups is the ability to pool together information that might be dispersed among many different people or from many different times. And then how do we use that information? Well, groups often, the smartest groups are ones that whose members think in different ways, process that same piece of information in different ways, or have different toolkits for using information. Of course, we all have biases as well as blind spots, and some studies indicate that we're better at identifying biases of other people than we are at spotting and reducing our own biases. Collective intelligence also works in the accumulation of knowledge over time. So groups often benefit from the knowledge and experience of their ancestors or predecessors. And then finally, if under certain conditions of independent judgment and sufficient number of people and diverse non-correlated errors, the crowd can be very wise. The famous example of Galton and the cow, but also in modern examples from prediction science. So these are all ways in which a well-organized, well-composed group can be better than even the best individual at solving a hard problem. But groups often fail to solve problems, and in fact, groups can often be less intelligent than their individual members. One is if they have incomplete information or are ineffective at aggregating the information they do have. If they're missing some important skills or expertise. If they don't choose the right process, it may be to solve this problem, they don't have enough structure in their process, or they have too much structure, and so there's a mismatch between the process and the type of problem. Sometimes groups have a bias toward consensus. So is the first option that seems to command some support. The group just converges quickly around that option, even though it might not be the best one. Sometimes groups suffer from weak facilitation. Facilitator lets the group get off topic or lets a few people dominate the discussion. And finally, groups can fail to reflect and capitalize on previous similar problems and reason by analogy to what could be a good solution now. These are some factors that can block the creation of collective intelligence. And you might have seen in previous videos, we've talked about different levels of complexity. The lower levels of complexity are the type of problems where collective intelligence tends to add the least value, where things are well framed, clearly solvable with a replicable solution, not much expertise required. There's a medium level of complexity we call technical complexity, which might be very well framed but still difficult, like creating a factory of water desalination. And finally, we have what we call wicked problems, which are often include lots of different perspectives and interests. where the problem itself, we don't have complete information, where the problem is maybe volatile, changing quickly. You've heard the term VUCA. These are types of problems where collective intelligence is really essential, where even the smartest person acting alone could not produce a sustainable solution. So, the first lesson here is, the more complex the problem in front of you or your team, the more you will need a good method of collective intelligence to solve it. And so let's think a little bit further about what a wicked problem requires of us. So the first thing about a wicked problem, like, let's say, motivating a large organization or opening an office in a new country where the culture might be very different, or solving a problem like racism or sexism, or managing natural resources, where there are lots of different perspectives on the problem, where we might not even have a common definition of what the problem is, and then interests might be in conflict, either apparent conflict or real conflict. And this is why one of the reasons why we need collective intelligence is because we can only make progress if we implement a solution together, if we work together. So there's not just the analysis part of the problem, but there's the mobilization. And this is why we need diverse coalitions with inspiring stories that mobilize. Wicked problems are complex and fast-moving. We don't often know what is causing what. We have important knowledge gaps. And so wicked problems require us to have channels and create new channels for data and feedback. Wicked problems might go beyond or require more expertise or more different types of expertise than we have currently. And so we need to create and develop entirely new sets of skills, going beyond what our team currently does. And then finally, there's no once and for all solution to a problem like a good organizational culture or equal rights for women. These are problems that will continue to evolve and are very unlikely to be resolved ever in an absolute way. And so this is why, instead of thinking about finding a solution for a highly complex problem, what we really need to do is to find strategies to make progress on the problem and design rituals of collective learning, so we continually update our understanding of the problem and update our strategy to how we can make progress on it. The most complex problems will not lend themselves to linear solutions. This is why we inspire ourselves from the example of Colonel John Boyd, famous American fighter pilot and strategist of complex problem solving. And he said, basically, in war, you can't use linear methods of problem solving because you're constantly faced with complex or novel situations. John Boyd put it this way: in war, time is the dominant parameter. The key to victory is the ability to create situations in which you can make appropriate decisions more quickly than your opponent, right? And because you're constantly in new and complex situations, this doesn't happen in a sync straight line. This happens in loops. So John Boyd created this famous schema called the OODA loop, sometimes with an extra L added at the end. OODA means observe. We begin by observing, taking in information. We orient, we interpret that information. We create a mental model of the problem. We decide what we're going to do. We take action. And then the final L is what we do over time, which is to learn whether the action had the right result. So this is something we encourage you to think not in straight lines of problem, solution, but rather in loops, right? Of new information, interpreting information, making decisions, taking action, and then being able to incorporate what you learn. So in this series, we're going to look at a couple concrete methods in which groups can identify, define, and deconstruct problems. These are the first three steps in our problem-solving loop. And this loop is a kind of adaptation of John Boyd's loop and of many other similar problem-solving schemata, where we begin by identifying from all possible problems we might be interested in what is the most high priority problem for right now, and then exploring what do we know about that problem, how do different people look at it, why is it important, what are the risks involved if we don't act in the right way. We're going to do a couple of of methods of problem definition. And then we're going to look at root cause analysis, also known as deconstruction. Once we have a better definition of the problem, then we need to explore why this problem is happening. And so these methods link together and this is just several of the many, many methods of problem solving that you could employ. But these are some that we think are especially interesting for groups learning to build their toolkit of collective intelligence. So we're going to start in the next video by looking at how to identify a high priority problem from a list of possible problems using a CI method called affinity mapping.